So is my screen visible to all of you?
No.
No, right. Okay, just a minute.
Yeah, now
Okay,
it's
is it fine? Ah, sir, good, very good. I think Ashutosh is also here. Okay, so
now it's there.
it's there, no? Okay, very good. So very hearty welcome to the course Combinatories, right? So this course we are going to teach jointly, Ashutosh and Professor Ashutosh and me. I think most of you already did some course with either with me or Ashutosh, right? Or Ashutosh is new. He is a new faculty who joined here not even a year ago, right? So,
Yes,
so what is the right, Ashutosh?
Yeah. Yes.
Okay. So would you like to say some words before we start?
So I'll just I would just show my face and just So you guys, some of you had made a request to me directly to be added to the course who are from different departments, and I have just added you to the Teams group, and I hope you'll enjoy the course. And so the first part will be taught by Professor Minty, the second part will be taught by me, and I have updated the course related things on my webpage. Professor Minty will also tell you about those things during the lecture. And yeah, if there are any questions or whatever, there is the course website. There we are available through email, so you can send us that. And yeah, I just want to wish all of you best of luck. That's all I have to say, I guess. Thank you, Minati.
Oh, okay, thank you, Ashutosh, for joining. Okay. So, I think some of you actually already, most of you did the discrete mathematics course with me, right? Before. So let's do this as follows. So if you are going to talk, so just show your face so that, I mean, I also can see your face, right? Because it's almost more than 1.5 years we didn't see each other. So it's a good idea to see you, right? Okay, and also I would like to make the class as interactive as possible, right? Though you know all that it's online lecture, so sometimes it might be difficult to interact, but it would be very nice if you guys also speak to me, right? Let me know your doubts and all, and also raise your voice if I am too fast or too slow, something like that. Okay, so don't hesitate to stop me. Okay, so first, as Ashutosh also pointed out, I mean, yeah, so the course syllabus is actually partitioned into two parts. Part one, actually, it's the part one, that part which I am going to cover. Okay, let me see if I write here also. Yeah. So this part,
Are you writing something, Minati? Because
right. I am going to write. So let me see. Yeah. If it is okay, good. Yeah. So this part I'm going to cover, and Professor Ashutosh will be covering this part, right?
Minati,
Yes, yes.
it is visible on the screen.
So is it visible? So maybe sometime I'll be using the right part of my notebook just for note. So is it visible? This part portion of the
just
code
the
is
note
visible?
coming, a blank white screen, and on top of that, the tools are coming, the pens, etc. But nothing else.
Okay. But this pen will be disappear anyway. If you can see the portion which I am actually focusing on, then that's right. Is it visible?
Yeah. So there
is it readable or something? Because if I hope most of you are in desktop or something like that, not in mobile. If you are in mobile, maybe it is too small to read.
I'm on desktop only, Minati.
Okay, so is it readable? I mean, can you read it? Or this?
No, ma'am, it's not readable.
Oh, it's not readable? I see. So, okay, let's make it bigger then. So, is it now readable? this small font, is it visible?
Oh, what are you writing? Where are you writing the thing?
That's so okay. I'm right. So this part visible? Whatever I am writing now. So, for example, I just marked tick marks, right?
No, ma'am.
It's not visible.
No, ma'am. It's
There
my
are
just blank screen.
like dots and there is one red line, but yeah, now the red line disappeared. Now another red dot appeared.
I see. So something. Okay. So okay. Just a minute. Maybe that. Let me. What I should do? Maybe I have actually. I opened two machines. So maybe that's the synchronization problem is going on in two of these machines. It could be the problem. So just hold on for a few
Yeah,
minutes.
you
I'll
can
be logging
do
out.
that and
Huh?
do that during
Yeah.
that
Yes.
and just talk like.
Right. I'll be just logging out and logging in.
Yeah,
Okay.
sure. So yeah, any questions or anything regarding the course? If you have like any initial questions, you can ask me now. And what else? Yeah, so there will be 12 lectures each in both the parts. They will be equally weighted for the exams and so on. So Minuti will most likely be taking a test and the minor. I'll most likely be giving an assignment and the major. And both parts will be 50-50 each. So 15 marks would be for the uh, test and for the assignment, and 35 would be for the minor and the major. So that is the course policy. We are not keeping any attendance policy for now. I mean, what for now? Not keeping because of the pandemic and most of you are not there. But we do expect that you come to the classes because it's nice to learn. I feel it's nice to learn in an interactive way. That if you can ask questions if you're not understanding something and so on. So yeah, I hope some of you or most of you agree with that and will come to the classes regularly. And the pass criteria is 30, both for credit and audit. We are not keeping it separate because in the end, anyway, we'll have to change it most likely. So it's 30 for credit and audit pass both. And yeah, that's more or less it. So in the first half, there are some holidays which will be covered by some other days which run on Monday or Thursday timetable, and then that you'll figure out. That shouldn't be very hard to do. That Professor Mintu will also announce. Any other questions? I mean, any questions? Till now, there have not been any questions. Okay, no,
Sir,
none.
can you repeat the mass distribution part? Like how much percentage of mass?
Say again, sorry.
The mass percentage, like 50-50. So how do we distribute it?
Yeah, so it is 50-50 both parts, first part and the second part. And the major and minor will be 35 each. So that is 70. Remaining 30, 15 marks will be a test. Most likely, Professor Mintu will take. And I will most likely give an assignment.
Okay, thank you.
Okay. Okay, so Minati is back. So
Yes, I'm back. But
there.
so there is some issue actually right now also. So what should I do? Because time is limited. So let's go ahead with my desktop machine. So because I was thinking to write something in my iPad also, so that I could not manage.
Okay.
Maybe something might happen. So what I will do rather, I'll share my desktop. Since it would not be difficult because I hope that most of the things are in the slides. But if I plan to write something, then that would be difficult to manage. Anyway, so let me see once again whether mm, I can share my screen. Share content. So there is one, okay, share my screen is this one, right? Okay, good. Maybe. So is my screen visible now to all of you?
It's coming. Yes, it's visible.
Yes, no? Okay, so good. Okay, very good. So maybe now is it visible?
Yeah, it's
good. So I think Professor Ashutosh already mentioned about some course logistics in the meantime,
yeah.
right?
You can go ahead with that, and
Okay,
I'll
good.
take your leave. And yeah, so I'll see you guys in the second half of the course, and Professor Minuti will take over now. Okay,
Okay,
Minuti.
okay, thank you, Ashutosh.
Bye. Yeah.
Okay,
Thank
bye.
you. Bye.
Okay, so in this course, mainly we will be referring to these two textbooks. I think the second one is already known to you, right? So we covered many things of combinatorics from the second book by Richard Gualdi. Okay, and sometime we might refer something from web pages, some lecture notes or something. Then I will be specifically mention that. So, for example, today's lecture is taken. Some part of the lecture is taken from lecture notes by Thorsten. Okay, so this is one key point. So don't worry. I mean, this will be available in our MS Team documents. Okay, I will upload that. So don't worry about it. Okay, very good. So this is the odds in the course. So I think the first two parts means test and minor. These are before minor. Then assignments and major will be taken by Professor Ashutosh, and audit pass is 30% overall. Okay, these are the odds thing. And of course, we have two brilliant TAs in our team, Shattam and Akash. Are they here? If they are here, maybe they can show the face. Are you guys here?
Yeah,
Yes.
I'm here.
Okay, okay. Please just show your face. That would be enough for.
Am I visible? Hello, I am Satyam Singh, of this course.
Good. And Akash is not here, is it? Okay, no worries. Uh, let's proceed. Okay, very good. So today's course is basically very, I mean, basic course, I mean, basic topic which we are going to discuss with, because this is an introductory course, introductory topic, and it's on combinatorics, right? So first question which I should ask all of you is, what is combinatorics and why should we study the course? So does anyone have answer to this? What is combinatorics, let's say? Because you guys already have some exposure on discrete mathematics. So no answer? Okay, so combinatorics is basically, so do you know mathematics? What is mathematics? Mathematics is arts and science, right? Combination of arts and science. And combinatorics is basically art of counting. Okay, it's nothing but art of counting. Okay, now the second question, which is very much important. I think I should ask you this question, and I should get the answer from you rather. Why should we study combinatorics? So, any answer? Shakshi? They're brilliant students, right? You are, I mean, some of you are very enthusiastic. I saw enthusiasm in discrete mathematics course, I remember. No voice? Who will answer this question? Why we are going to study combinatorics? Shakshi, can you answer this?
I think it has a lot of applications in theoretical computer science.
Okay,
Um,
good, good. Any other answer? Good, very good. So, any other answer? For example, Bhumika. I can see Bhumika. I don't see many. Okay, maybe here you are hidden, right? Uh, so maybe I can see Bhumika. Bhumika, can you? So as I mentioned already, if you are going to say or speak something, just make sure that your face is visible, because this is introductory. I mean, course at the past course, I should know each other, right? We should know each other. We should see your face, right? Bhumika, do you have any answer? Other answer than that? That this course has some application. Means combinatorics has some application in computer science. No, we can't hear Bhumika. Okay. Okay. Akash, do you have any answer? No, nobody is going to answer. Okay, so is it a silent course then? I was expecting more voice from your part, at least for today.
Ma'am, it can be used in probability, like the concepts are used in probability.
Good, thank you, Pratik. Yeah, it can be used in, the idea could be used in probability, statistics, right? And more specifically, the combinatorics, though the course, basically the topics, the subject, it was not at all one, what should I say, it was not a structured subject before 20th century, though people used to study combinatorics for, what should I say, it started with game, recreation problem, something like that, right? But later on, people found, I mean, it tremendous application in other fields. For example, it started from physical sciences, then you will see some application in biological sciences, right? And of course, computer science, information technology, and blah, 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 right? There are so many fields where basically combinatorics is very much important. And it has application, that is, of course, that's the beauty. But another part is it's also fun, right? So it's, as I mentioned, it's nothing but art of counting. So you are learning how to count something, right? So it's a fun, and if you love the course, I mean, then you'll actually love the concept, right? And then only the ideas will be there in your mind and heart for a long time, right? I would expect that you will love the subject from the beginning, so that you don't have to struggle further. Okay. Okay, very good. Let me. Okay, this is again. The screen is now. Good. Very good. Okay, so now the question is, what type of questions we are actually asking in combinatorics, right? So as I mentioned that, yeah, we also found some social science also has some application for combinatorics, okay? Apart from biological, physical science, probability statistics, and computer science, social science also, for example, social networks, right? Those are important things. Okay, now let us come back to the combinatorics. What combinatorics is really, right? So, and which type of questions we are going to ask in combinatorics, right? So maybe, I mean, you have some vague idea that combinatorics is concerned with arrangements of objects, right? Of a set into patterns, satisfying some specific rules, right? So this is vague, abstract thing. Now, to be specific, as I mentioned, I mean, for example, let's say we want to make an arrangement, sitting arrangement. Let's say we have a circular table, and let's say we have n many people, right? Some of them are men and women, both type of people are there. Now we want to make an arrangement of them, so that make sure that no two females sit side by side or adjacent to each other, right? So these are the specific rule which we are making, right, to make the arrangement. Now, sometimes it might not be possible, right? And sometimes it is the possible. I mean, it is possible. Now the question is, which type of questions we are asking in the combinatorics is basically mainly broadly two types of questions which we ask. Does there exist some such arrangement satisfying those rules, right? So this is the first question which people will ask in combinatorics. So this is known as existence. Okay, and okay, so if it is possible, now the obvious question is, what are the sufficient and necessary conditions, okay, to have such existence? Okay, that's the second question. It's all about existence. Now, if you have some existence, how to find? I mean, if you have some arrangement satisfying such and such rules, now the question is, how will you find such an arrangement? So these are all questions about existence. Okay, so this is the first type of questions which people, ask in combinatorics. And of course, the second question, which is very much obvious, is, let's say we know that certain arrangements are possible, right? Now the question is, how many such arrangements are possible? Is it that, can we say that, okay, there are at least this many possible, this many arrangements are possible? Or can we say that at max that many arrangements are possible? Means, can we give some lower and upper bound over the arrangements? Or can we say exactly that number? Then that is the great thing which we can actually, if we can answer the third question, exactly giving the number, right? So this is known as enumeration. Similarly, we might be actually, we might want to see all the arrangements, right? So then the question is how efficiently you can generate it. Okay, so this existence and enumeration, both the things which I just mentioned. So these are basically two abstract way I have mentioned, right? Now let's see with some couple of example. Maybe it would be very much clear to you if we illustrate this with example. So I hope everybody know the chessboard, right? So 8x8 chessboard is known to you. So let's consider one generalization of the chessboard, which is, let's say, one rectangular rectangular board having m many rows and n many columns. Okay, so m cross n rectangular chessboard we have, let's say. And what is domino? Domino is basically 2 cross 1 rectangle. For example, this is one domino. Okay, now the question is, can you cover given one chessboard or some rectangular board basically, and let's say we have infinitely many dominoes given to you. Now the question is, can you cover the chessboard with those dominoes, okay, perfectly? So what is the meaning of perfection here? So here it means we don't want dominoes to overlap when we are going to cover the chessboard, right? And also there is no, we should not place dominoes diagonally. Diagonal placement is actually prohibited. So these are the rules, huh? And of course, there should not be something like protrusions. Means some dominoes is actually, if some part is inside and some part is hanging outside, these are not allowed. Okay. If now, and of course, all the squares in your chessboard should be covered by some dominoes. Okay. So this is also known as covering as well as tiling. Okay. So now the question is, given any chessboard of, let's say, m cross n chessboard, the question is, existential question is, can you do a perfect covering by dominoes, right? So that's the existential question. Okay. And of course, the question is when it is possible. So as I mentioned, so in the existential question, we are going to ask existence, whether it is existing there exists something, and for which condition it exists, right? For example, for what values of m and n, we can guarantee that there should be a covering of a rectangular chessboard with m cross 2 cross 1 dominoes, right? And if it is possible, how many ways you can cover the chessboard with dominoes, right? So these are the first question is basically existential question, and the second question is basically the enumeration question. Okay, now let me ask you the question. So I am just showing you one question. Let's say I have m cross n rectangular chessboard. Okay, so can you tell me what is the necessary and sufficient condition that 2 cross 1 with 2 cross 1 dominoes you can actually cover perfectly one rectangular chessboard? What are the sufficient and necessary conditions? Can you tell me?
Ma'am, one of M or N should be even.
Right. So that's the necessary and sufficient condition, right? So can you
Yes,
prove
ma'am.
it? So it's good.
Yes, ma'am.
Who answered this question? Good. I love to listen your voice. So just tell me your name also when you are going to speak. Manish.
Yes, ma'am.
Good, very good. So okay. So can you prove this? Prove your statement. How? So let's say. So for example, we are actually speaking two things, right? We are saying that if either of m or n is actually divided by 2, then basically you can make a tiling, right? And also the same thing, let's say I have a tiling with 2 cross 1 dominoes, then either m or n is divided by 2, right? These are the two statements you need to prove, right? So can you prove, how will you prove such thing?
Ma'am, first of all, I want to prove it in 2 steps. In one step, I'll take both M and N to be even, and in one step, I'll take one of M or N to be odd. So if both M and N are even, then we can divide the whole chessboard into rows of even lengths, and all of them can be placed with 2 cross 1 dominoes perfectly. So that means both even is simple. And if it is odd, suppose m is odd and n is even, then we can divide this whole board into m minus 1 cross n and 1 cross n different boards.
M minus 1 cross board means?
M minus 1 cross n.
M minus 1 cross n board. Okay.
And 1 cross n board.
Mm-hmm.
And now the 1 cross n board is a board with even number of tiles of row 1. So that can be easily set with dominoes of 2 cross 1.
Mm-hmm.
And the m minus 1 cross n is a board with both even dimensions.
Okay, good. Yeah, so this is one way to prove. Right? One way you have to means given that you either m or n is even, then you can actually make a tiling. Now, how would the opposite? That is actually simpler, right? If you have a yeah, so how would the opposite direction?
Ma'am, what's the opposite direction?
Opposite direction means, let's say I have a chessboard, right? M cross n chessboard, and a tiling with m cross 1, sorry, 2 cross 1 domino is possible. I mean, it's given to you. Now you need to prove that either m or n is divided by 2, right?
Yes, ma'am. So if this is not true, then since the total number of blocks that can be covered by, let's say, T blocks will be 2 into T, but the total number of blocks here are M into N, which is odd.
Right. So it's simple, right? So yeah, thank you, Manish. It is nicely you have actually argued it. Very good. So now let us actually generalize it. So in combinatorics, as I mentioned, there are two types of questions, right? Existential questions. Another is enumeration question. So the next question, which also people see, is basically generalization. So you prove this your statement with 2 cross 1, right, domino. Now let us consider k cross 1 polyomino, right, polyomino. So now can you actually generalize your statement? So the claim is, let's say, as follows. We are claiming that we have, let's say, m cross n board, and it can be tiled with polyominoes. This is one, it should be 1 cross k. Okay, so instead of 2 blocks, in domino we have 2 squares, right? And in polyomino of size 1 cross k, you have basically one row having k many squares. Okay, so now the question is, can you always tile one m cross n board with polyominoes of size 1 cross k, right? And the answer is, our claim is basically you can tile if and only k divides either m or n. Okay, so now can you try to prove this statement? This is again, I mean, it's a generalization, right? We are generalizing whatever we have in our hand. We are trying to generalize it for higher, I mean, something more structured. Okay, so can you generalize it? How to prove such statement? Okay, so as I mentioned, I mean, in the previous proof also, we have here also we need to prove two statements. One is, let's say we know that k divides m, okay, or n, anything. Let's for the without loss of generality, let's assume that k divides m. Okay. Sorry, k divides m. Let's assume that. So now, can you give a construction of tiling if you know that k actually divides, let's say, m? Okay, if you can do that, then basically you are proving that if k divides m or n, then basically there is a tiling with polyomino, right? So now you need to prove the other way, right? Once you have the proof for that, the next question is, what statement you need to prove? For that, you basically need to prove that, let's say, if we have a m cross n board that can be tiled with a polyomino of size 1 cross k, then that implies k divides m or n. That you need to prove, right? Right. So let's instead of proving that statement, we can also prove the contrapositive of that statement, right? I hope you have remembered contrapositive thing. which you learned in discrete mathematics, right? So what we are going to prove, rather, we are going to prove that let's say k divides none of them, neither of m or n. Okay, now we need to show there doesn't exist any tiling with polyomino of size 1 cross k. Okay, that you need to prove. Okay, so you have, I hope you have understood the logical consequences of this, right? If you are going to prove this statement, then only the claim is true. Now the question is how you are going to prove it, right? Can you tell me the first steps, means first arrow, first direction at least? How will you prove? Let's say we know that k divides m. Is it easy construction for tiling? Can you?
Yes, ma'am, we can divide it into n rows of length m. And we
Right.
can,
Right. So since m divides, sorry, k divides m, so what we can do, m cross n board, right, we have. So we can basically divide the whole board into many, after m many rows, right? So, and fill those m many rows by just your tiling, the vertical order, right? You just put all the polyominoes over there and copy this, right? So in this way, you can actually get one easy to get construction for tiling, right? Is the picture clear to all of you? I'm sorry that I don't have this iPad over here to show you the drawing and all. Let me, okay, where else we can draw? Any idea? Okay, I hope you have understood, right? How you are getting this?
Yes,
Everybody
ma'am.
understood?
Yes,
Everybody understood? Okay, good, very good. Because this is very straightforward way to tile it. Okay, now the question is how you are going to prove the other way, right? The opposite direction, how you are going to prove it, right? So that proof is basically, it's not that much simple. It's tricky. It's not difficult. It's just a tricky. Any idea how you can prove the other direction? Any idea? Any idea? Manish, will you try?
ma'am, I'm thinking about it.
Okay. Okay. Think about it then. Okay. So what we can do? Maybe it's a good idea. Try on your own. So if the answer is not that much, I should say it's not difficult. It's just tricky. You think on your own. I will come back to this answer later. Okay. Because okay. Now let us do something else. For example, we need to actually draw something. That's why I am going forward. We'll come back to this answer. Think on this, think over this question in the background. We'll come back to the answer, okay, towards the end of the lecture, maybe. Okay, now the next question is, as we mentioned, so far what we have learned in combinatorics is basically, I'm repeating, right? So this is basic lecture, as I mentioned. So combinatorics is all about counting, and the two main important aspect is which type of question we are going to ask is basically existential question, and second question is basically enumeration question. So is it all what we need, right? No, the answer is no. So there are other aspects of combinatorics also. So let's say I have some arrangement, for example, this chessboard and all, right, with dominoes or polyominoes, these arrangements, right? We have studied the numbers, means existential thing we have studied, and also the enumeration thing we have studied, let's say. So the next question which we are going to ask about is basically classification. So you can understand that you have basically for the time being, you can see there are many ways to arrange one. If it is possible to tile one chessboard with some polyomino, right? It might not be a unique arrangement. There could be many arrangement possible, right? So for the time being, let's assume we have actually many arrangements possible for the satisfying specific rules. So now the next question to ask is, do some of these arrangements differ from others in a particular way? Okay, this is the question which we ask. So this is known as classification. In other words, is there any natural partition among all these arrangements into specific class? Okay. So can we classify these arrangements? So we have so many arrangements possible, let's say, for tiling your chessboard. It's not unique arrangement, right? So now the question is, can you classify these arrangements, right, nicely, right? So that's the question. So let's do for example, I mean, for the example purpose, let's see this concatenation of two chessboard. Okay, so for example, so the left hand side you can see, okay, we have 4 cross 4 chessboard. Okay, and in the right part also we have 4 cross 4 chessboard, right? And they are concatenated by just 2 square, this white square and this black square. This middle one is basically, it's a hole. Okay, this is also one chessboard just with a hole. Okay, is the chessboard making sense to you? Did you understand the position of the chessboard?
Yes, ma'am.
Yes, right. So we have just this white one is basically whole. Other than that, it is everything is there. So basically now it's 4 cross 9 chessboard, excepting this hole. Okay, now let's try to tile or let's try to cover this whole chessboard using dominoes. Okay, for example, we need to start from somewhere, right? Let's try to do this. Let's put 2 dominoes here. One is here and another one is there. Okay, now the question is, can you cover this whole chessboard with this starting configuration? Can you cover it? That is the question.
No, ma'am.
No, right? What is the answer? I mean, what is the argument? You need to give me some argument. Yeah.
I'm like any domino which we place now, it would either be in the right half or the left half, and
Right.
each of them have odd number of squares left.
Right. So great. So who answered this question? I'm happy.
Shravan.
Shravan. Thanks, Shravan. Yeah, it is perfectly correct answer. So basically, I hope you got what Shravan told. So basically, if you are going to put these 2 dominoes here and there, right? This one and the other one, then basically, if you may consider this whole chessboard as 2 disconnected smaller chessboard, right? Where basically the left part has this bottom bottom right square is missing, right? And for the right part of the chessboard, 4 cross whatever we have, 4 cross 4, right? For that actually this top left corner जो square है, that is missing, right? So now in both of these 2 disjoint chessboard, right, you have odd number of squares, right? So if you want to cover them, then basically with a domino, right, we have already proved that either m or n should be divided by 2. But yeah, that rule is that is not true here. I mean, we have just one thing is gapping, right? So it should be divisible. This whole number of squares should be divisible by 2, right? Which is not true. So you can't basically cover the rest of the thing with this starting configuration. Okay. Okay, now as you understood that if we are going to cover the whole chessboard with this starting configuration, it is not possible, right? Now the next obvious question is it at all possible to cover this whole chessboard with dominoes?
Yes, ma'am.
Yes, right. So how will you do that?
We'll put both the tiles we put right now, we should put them on the same side.
Right, good. So good, very good. So that's basically, so now you consider all the arrangement possible. So it's not that there is only unique arrangement possible, right? As I mentioned also previously, right? There are many arrangements possible with such thing. So the only thing which we need to do is basically you need to start with both the, I mean, this the extra whatever this white and black you have, the joining, concatenating purpose, whatever the two squares you have in your hand, both the squares you should give to either right side of your board or to the left side of your board for placing your dominoes, right? So in other words, you can classify all the possible arrangements for the tiling, right, in two distinct part, right? One or two distinct class rather. You can partition it, right? One class will contain all the arrangements where basically these extra squares belonging to the left side, right, matches to the left side, and another type of arrangement where these both of these extra squares are given to the right side, right? These are the two partitions, right? Do you understand? So this is nothing but classification. So you are classifying all of your arrangement into two classes, right? And having this property, using this property, right? So this is just one example. This is not the only way to partition or classify your all arrangements, right? All possible arrangements you can actually partition using some different way. Also, you may partition. For example, let's say I want to, if it is possible, so it might not be possible for this board. Consider one 4x4 chessboard. Okay. Now, basically, you can and consider all the arrangement possible to cover the 4x4 chessboard by dominoes only. Okay, so there could be many possibilities of arrangements could be there. Now, let's say we want to classify them. Okay, how will you classify? You can actually see some of the arrangement, I mean some of the tiling, in such a way that you can always draw one horizontal line, of course, along your boundary of the square, some of the squares, such that it doesn't hit any of the dominoes. Okay, it might be possible in some of the arrangement. In some of the arrangement, it is not possible, let's say, to draw the horizontal cut, but it might be possible to draw vertical cut. Okay, and some of the arrangement, it might be possible that you have both type of cut, horizontal or vertical cut. Now you can actually classify all the arrangements. It is actually, it's known fact that you can always have in 4x4 chessboard, and if you are going to tile them using dominoes, it is always possible either to have horizontal cut or vertical cut or both. Okay, so using this idea also you can classify your all arrangements, right? So this is nothing but this is the classification part of combinatories. So combinatories is also concerning about this classification thing. Okay, does it make sense to you? Do you have any questions so far? I hope you have understood, right? So apart from existence and enumeration, combinatories has to do something with classification also. Okay, so this is known as classification. Okay, now let's move to some other aspects of combinatories. So it's as I mentioned, combinatories is not only about existence, enumeration, it is also classification. So it has also something to do with meta structure about your arrangements. Okay, so what is that? What is the meaning of meta structure? Okay, now you know that, let's say you have so many arrangements, right? Now the question is, do the arrangements even carry a natural underlying structure? Means, is there any ordering you can order among those arrangements? Okay, or maybe when are two arrangements, when can you say that these two arrangements are closer to each other? Rather, we have some different arrangements, they are actually very distant from each other. Okay, so can you say something like that? So these types of questions are also, I mean, part of combinatories. Okay, or maybe is it the case that are different classes of arrangements in a they are in a particular relationship or not? Okay, these type of questions are known as meta structures questions. So that is also part of combinatories. Okay, so for example, it is a vague thing, abstract thing. Let's do with some real example. Okay, now again you come back with your tiling thing. Let's consider we have a chessboard with 4x4 chessboard. Okay, only we have 4x4 chessboard. Now we are, so you know that there are tilings are possible with dominoes. So let's consider tilings of using dominoes. There are several, I mean, several ways to do that. So now the question is, now we are actually giving some definition. Let's say we have two tilings. Okay, we are saying that they are adjacent to each other if you can transform one arrangement to the other arrangement by doing something called turning the, what should I say? Let's say you have two dominoes which are actually which are which are like lying like this, right? And you can turn, or maybe what should I say, they are actually lying like this, right? Now you can you turn it and make it upward. Okay, you can turn both of them together and make it upward. It's still a valid arrangement, right? By dominoes only. And let's if it is possible, then we are going to say that these two tilings are basically adjacent to each other. Okay, for example, let's consider it's a very small figure. I hope you will be able to see it. We have a tiling of 4x4 chessboard, okay, using domino. This is one tiling, right? And you can see just below it there is another tiling which we have obtained by using this turn operation once only, right? Once. So you have just turned this middle two dominoes. So they were lying before, now they are lying upward. So they were lying like this side by side, now they are basically upward side, right? And if you make that, then basically you are getting another arrangement. So these two arrangements are basically next to each other. So basically, so in this way, basically you can see this graph. So where we have actually drawn, we have given edges if they are basically adjacent to each other, and the figure, the graph looks like this. Okay, you can see, you can have a look at it. It's very easy to obtain this graph. Okay, so now let's define distance between two tilings. Okay, so what is the distance? Obviously, in the graph forms which we are going to define it, right? So we are saying that let's say I have a tiling, for example, this one, another tiling is this one, right? Now the how many turn you need to do to go from that one tiling to another, right? So that is your distance, let's say. Okay, so basically you understood, right? The distance metric, the distance function, how we are defining it over this arrangement, that you have understood, I hope. For example, from here to there, you can actually reach from here to there by actually turning two, by doing two turning operations, right? One is just make this one was like this, now you make like this, so it will happen like this. Now you, if you want to go from here to there, the second one, right, then basically you need to do the top left corner, jo side by side, those two dominoes, whatever you have, you just make them like this, right? So the distance between this one, I hope my cursor is moving and you can see it, from here to there is basically just two turn operation. So now the obvious question, I mean, which we can actually ask is basically, you consider all pair of arrangement, right? Now, what are those pairs for which the distance is maximum? Okay, for example, you can see this is a very beautifully, I mean, drawn figure where basically from this, the top one and the bottom one, they are basically the farthest from each other. Okay, they have the maximum distance in between them. Is it true that they have the maximum distance in this graph? Is it true? So do you understand the graph, right? I mean, at least you saw the graph. You don't need to. Do you understand what we are talking about? Did you see it? First of all, did you understand what we have defined the distance function? given two arrangement, right, or two tiling, right, what is the distance between them? So we have defined one turn operation, right? So you can also define your own turn operation. I am not saying that this is the only turn possible, right? So now the question is, in how many turn you are going, you need uh, to reach from one arrangement to another, right? So that's the basically that's the natural way to define the distance between tilings, right? So you can see, so in this way you can actually say that who are the tilings, means which are the arrangements who are basically very close to each other, right? So for example, those who are adjacent to each other, they are the closest one, right? And those pairs are the closest one, right? And as far as you go or walk in this graph, right, as the distance is increasing, so they are basically far from each other. So this type of thing, this type of questions are also part of combinatorics, and these are known as metastructures. So right, so let's go back to the question. So what is metastructure? As I mentioned, so is there the main question which we ask in metastructure is basically, is there any underlying natural structure between the arrangements? And can we say that these two arrangements are closer to each other than to others, right? Or similar than some other pairs, something like that, right? So these types of questions are also part of combinatorics, and this is one example of that. Okay, so this is not all about combinatorics. We also have some other questions which we will ask in the combinatorics course. For example, the next question is optimization question. Okay, for example, here, as we said, right, with respect to this distance function, we ask the question, what are the pair for which the distance is maximum, right? So this question is nothing but optimization question, so, right? So that's why, so this type of questions are also part of combinatorics. So in other words, in optimization on all, so there also combinatorics plays a vital role, right? Right. So let us see what type of questions we ask in optimization with respect to combinatorics, right? So now let's say, assume that we have some arrangements, right? They differ from each other by some measurement. So the measurement, it is the distance measurement which we define. It is not the only distance measurement. There could be other distance measurements also. You need to define, or maybe, I mean, depending upon application and all, people will define, or maybe not only application. So as mathematician, we sometimes forget about application. We just do this for the sake of, what should I say, for the sake of fun sometime, or recreation purpose also. We sometimes define it. Right, without having the mind that, okay, that might have some application later on. Okay, so you can define some distance measure, right? So now, as I said, that is not the only distance measure. There could be some other distance measure also. And the question is, can we find a character? Can we find or characterize the arrangements with maximum or minimum measure, or something like? Can you say that this is the best arrangement with respect to some measure? Okay, some measure, or this is the worst arrangement with respect to some measure. Okay, so let us see with another example. The question of optimization will be clear to you with another example. So now let us define decreasing free paths. Okay, I hope the screen is visible to you. Is there any question so far? So I am only talking, you are not talking anymore. Is there any voice? Any question? Anything? No question? Okay, good. I see. Okay, so now let us come back to again the let's consider any chessboard, and again let's say they are actually, I mean, consider any arrangement, or rather let's consider one tiling with domino. Okay, now we are going to define decreasing free paths. What is that? So a path which starts at the top left corner of the board, okay, and it is monotonously proceeding from that top left corner of the board to the bottom right corner, okay, without cutting any dominoes, right? So and it should be monotonously, means it should not be the case that this path is going here, then it is coming in this left direction. It should not be like that. Okay, so I hope you know the monotonicity, right? So this type of path is known, let's say we are defining this as a path which is a decreasing free path. Okay, so given any arrangement or given any tiling over one chessboard with domino or polyomino, you can define such decreasing free path, right? I hope you have understood the meaning of decreasing free path. Okay, now of course some tiling will admit more such decreasing free path, and some tiling will admit they might have very few decreasing free path. Okay, it's not that all the tilings whatever you have or all the arrangements whatever you have over some specific chessboard, it's not that all of them has same number of decreasing free paths, right? So this is one example of decreasing free path. You can see in this figure itself, I can have another decreasing free path like this, right? I might have another decreasing free path like this, right? There are several. So now the question is, in which tiling the maximum number of such path is attainable? Okay, so this is the question of optimization. In which type of tiling, in which particular tiling you have maximum number of such path, such decreasing free path. Does the question make sense to you, this optimization question? And can you answer my question, this last question which I asked? Can you answer it? Manish, will you answer this question? Or Shravan, will you answer? Shakshi, Harsha, Bhupender, I can see all these names. So can you answer this question? First of all, did you understand the question?
Yes, ma'am.
Okay. So now the question is, in which tiling the maximum number of such decreasing free path is possible?
The one on the right.
The one on the right, okay. Okay, so that's good guess basically, yes, and the correct guess is right. But can you prove this? Can you prove this? So that's the next question. And unfortunately, we don't have any answer so far. It is conjecture only that yes, if you have a tiling like this, there basically the maximum number of decreasing free paths are possible, but it is only conjecture. No proof has been found for this particular problem so far. Okay, so it's open. Maybe you can think about it. How will you prove that such statement that in this particular type of tiling, that is the arrangement for which you can attain the maximum number of decreasing free path. So this is optimization question, but you need a hold on combinatorics to answer such thing. Okay. Do you have any questions? Do you have any
Excuse me,
questions? Yeah.
has it been verified for any small values of m or n such that this styling is optimized?
Right. So that's a good question. Maybe you can try to prove such statement for 4x4 or 8x4, 8x8 matrix. Maybe for small tiling, it may be something is known, but for this general m cross n chessboard, it is not proved yet. Okay. This is very simple to visualize question, right? Optimization question on combinatorics, but we don't know the answer so far. Nobody proved it yet. Okay, any other questions? So let me actually summarize whatever we have mentioned, what is combinatorics all about, right? So far what we have mentioned is basically something like this. Combinatorics is the art of counting, right? And it's art. That's why you need to have some, what should I say? You should have some aesthetic sense, right? Right, to learn and love combinatorics. So, and combinatorics is mainly concerned with existential question, enumeration question, classification, right? Meta structure, and last question is optimization, right? These are the main questions which we are going to study in combinatorics. And so of course we need to, if we need to look at all these types of questions, it's not the case that there is only some unique tool is there, something like that. It's not the case. You need to invent some tool. So some known tools are there, of course, in the literature. So those things which we are actually going to cover here.
Excuse me, ma'am.
Yes.
Ma'am, in the general M cross N case, the arrangement need not be the one with horizontal tiles, right? It could be
Right.
vertical as like it
Right,
could be
right.
either one of them.
Okay, right. In the vertical also, right. It is, as I
Like,
said, it is actually, yes, like this or that. Okay, it is just conjecture. Conjecture. Nobody has proved it. So you may disprove the statement also. Okay, it's not proved yet. You may disprove the statement. Okay, and or you may try to prove it also the other way. Okay. Okay, so these are the main questions which we are going to look at in combinatories. So, okay, I hope you have understood some of the things. Now let's go back. Since we have some times, let's go back to the question which we raised, and I hope you have got some time to answer the question, right? To think about this question. This is the some tricky answer we need, tricky argument we need. So have you understood the question? Let me again reframe the question. So the question is as follows. Assume K divides neither M nor N. Now show that if that is the case, then given any M cross N chessboard, you cannot tile that board. It is not possible to tile that board using one polyomino of size 1 cross K. Okay, so that's the statement which we need to prove. Okay, any idea how to prove? Since I have some time at least, so any idea how you prove such statement? This is, you need some tricky thing. At least
Ma'am,
try.
you can
Yes.
color the chessboard into k colors such that each polyomino covers exactly one square of each color.
Acha, this is good. So this is again Srivas. This is new face, I think, Shubhan. So as I mentioned, you should also show your face. That would be good for me also. Otherwise, I saw your face 2 years back, right? So I would like to see your face again. That would be good for both of us. So just show if it is possible, of course. Otherwise, not. Yeah, Shubham. Yeah, your approach is correct. You're in right direction. Yeah, thanks, Shubham. Yeah, good, very good. Okay, so as Shubham actually pointed out, we can actually color the board, right? So how we are going to color it? Any idea, Shubham?
Like we could start from the bottom left corner and color it with color 1, then move towards the right and color it with color 2, and so on till color k,
Okay.
and then again color 1, color 2,
Okay,
and
then
then
right, good,
to
good,
the
good.
second row, then started with color 2, then color 3, color 4,
Good,
and so
good,
on.
good, good, good. So you are actually, yeah, you are in the right direction. So you will answer the question. Okay, you will give the answer. So as Shubhan pointed out, we can color the chessboard like this, right? As you mentioned. So let's say this is the K is, let's say it's 6, right? Let's say K is 6, and the board is 8 cross 9 chessboard. You can see 6 divides neither 8 nor 9, right? But 6 is dividing 8 cross 9. Okay, though 6 is dividing 8 cross 9, but 6 is dividing 6 doesn't divide 8, it doesn't divide 9, right? Now basically, and you can color as Shubhan pointed out. Let's say the colors, okay, 0 color 1 is basically, let's say, white color, and this is the off white color is basically color number 2, let's say 3 4 5 6. I have 6 colors. Color 6 is basically, it's for black. Okay, let's say, and we can color the way which exactly Shubhan told. Means I we will color this chessboard with this is a block of colors 1 2 3 up to 6. Then I am going to repeat that color for that row, right? And for the second row, what I am going to do is basically I am just shifting, okay, shifting the position of the start. Okay, so shifting the position of the start means the white, for the first column, it was the first position of first for the first column, the position of white color was the beginning, right? For the second column, what I'll do, I'll start the white color from the second row onwards. Okay, here. right? So I'm just shifting one square and doing this repetition for all other blocks. Okay, and cycling, it's in cyclic order we are actually doing something like that, let's say. You understand this coloring, right? Now the question is, in with which color you are going to color the topmost guy in the second column, right? I will be coloring with the color 6. Okay, and if for example for the third column, so the white is here, right? Now the which color you are going to use for first position and second position of that third column? So fifth color and sixth color you can use, right? So for example for the next fourth column you can actually start with so it was 4 5, so now you got 3 4 5, right? Sorry, 4 5 6, then 1 2 3, like this. So this is one coloring, right? Okay, now question is, as Shubhan pointed out, what you are going to do with coloring, Shubhan? So once you have this coloring, the question is how you are going to use this coloring to prove your statement. So this is
So
just a
each
coloring, right?
polynomial will cover exactly one square of a particular color.
Okay, I think it is hang. I didn't listen. I couldn't listen, Shubhan. Sorry. So what do you say? Can you repeat that?
Saying that each
Uh,
polynomial would cover exactly
uh,
one square of each color.
right. Yes. Good. Right. Then, yeah. Do you understand what Shubhan is saying? So after giving this coloring to this chessboard, right? Now you consider any placement of your domino. Consider, sorry, not domino, polyomino. K 1 cross K polyomino. You have one cross K polyomino. Now you can place. You just try to place it somewhere, right, some position. Of course it should not be like diagonal or something like that. So you'll see all the 6 colors should appear in that in that polyomino, right? All of these colors should appear, right? So that's a beautiful observation. Okay, I would say this is the beautiful observation. Now the question is how you are going to utilize this observation to one. Okay,
So
yeah,
some
that's
of
the
the
observation.
colors,
Yeah.
so they are like, suppose color 1 would have some 7 squares covered and color 2 would have a lesser number of squares covered.
Right. So that's the beauty. Yes. So now, yeah, why that is the case? Why color 2 is less? If m is, sorry, if k doesn't divide m or n, then why color 2 is less?
Because if we look
That
at
you need to argue, right? That you need to argue. Then you're done basically, right?
if we look at any particular row, there would be more squares of some particular colors because K
Okay.
does not divide M or N.
Okay, right, good. So that's also observation, right? You need to prove your observation. Yes, what Shubhan told is perfectly correct. So how you can prove it? Something like this. So you have a chessboard, right? M cross n chessboard, and you know that k doesn't divide, neither divides m, nor divides n. So what you can do? You can actually partition this whole chessboard uh, using k cross k block. Okay, right, Shubhan? For example, here you can actually partition this is a small thing, so you have this. So now you can see, you consider, you can see if you have already k cross k block, in each of those k cross k blocks, so all the colors has actually exactly same number of times appearance. Okay, so for them we don't have any oddness, right? Now consider any to be specific, consider one block which is basically this right bottom right corner, do we have, right? You can see the number of colors white is more than the second guy's color. Okay, right? Second guy's color जो भी है, you can see. And here also, that's whatever the smaller portion you have here, also you can see the number of colors white is actually more than the second colors of white color, whatever you have, or same. So at least for the topmost, either they are same, or at least for the bottom right corner, that small partition whatever you have, for that particular block, you have more white than the off-white one, means second color. So if that is the case, then you can understand. We have first observation. What was the first observation by Shubhan? As Shubhan mentioned, that if you are going to place one polyomino, it should have k distinct colors, right? Whatever way you are going to place it, that is the particular thing. So now if you are going to if you are able to make arrangement with polyomino, then basically you since this is a perfect tiling, right, it should be that for each of the polyomino you are actually putting there, for each of them same number of color, I mean each colors are distinct, since so basically it should be the case that all of the colors, number of colors should be same, right? Each color should appear same number of time, but unfortunately it is not true. You can see the total number of white color is more than the second number of color if k doesn't divide m or n, right? So in other words, it's not at all possible to tile your chessboard with polyomino if k doesn't divide m or n. Okay, does it make sense? Thanks, Suvan. Yeah, it was approved by Suvan only. I just made the I just connected it. Yeah, good, great. That's it. Okay, is there any other question do you have in your mind? Okay, I think if not, I should discuss some other question. I mean, yeah, other things. So, for example, yeah. So, so this is the today is the beginning class, right? The first lecture, and it is actually completely introductory lecture. Next meeting would be again on Thursday, same time. Okay, and I hope that by that time I will also be able to work with my iPad so that I can write something if it is needed. Otherwise, only this desktop is not enough. Okay, do you have any other questions? Do you have any questions?
Ma'am, the audit pass total is cumulative
Yes.
30%, right?
Right. It is cumulative 30%. Yeah. Audit pass is total 30%. You don't have to. I mean, there is no breakup like that. And right. So before so I'll teach up to minor. So the before minor, we'll try to have one test of 15 marks, and in the minor one, there will be 35 marks minor one paper. That's the difference. Otherwise, I mean, I think minor is not that much, since we have only one minor, so we had to do this. Okay. And the topics which we are thinking to cover, at least, yeah. So my part, I'll be covering this principles of inclusion, exclusion. So these are the basic things which you know already. Maybe what I'll do, I'll spend one lecture over inclusion and exclusion, where basically some parts which we'll revise, and some of the questions which I will put, those might be new to you, because I know most of you know this what principles of inclusion and exclusion is, right? And the last part is basically these three things would be new: projective and combinatorial geometries, Latin squares, design of Steiner triple system. Those parts would be new, completely new. And there you will see the thing which we actually discussed today. I mean, which type of question which we are going to ask there. Okay. Okay. Do you have any other questions? If not, maybe we can conclude today's session. So today we are fast. No question. No question. Okay, then maybe let us conclude today's session if you have no questions. Okay, thank you in that case. No questions? Should I wait? Okay, bye then. Have a nice time. Okay, bye.